Yeah. Yeah.
It's they don't smell fun.
Oh.
Yeah. They do.
Yeah. So I hinted the last time that we were going to talk about local bond theory versus molecular orbital theory. So today's the day. And so we're going to go in, we're going to compare these two theories just to refresh your idea of their differences. And then we're going to get to the evidence that supports them. Okay. And so the local bond theory, also called valence bond theory, that's the one we've been using this whole time in making our 3D shaped molecules and the flow chart and all of that stuff. So it obviously works pretty well, or we wouldn't be able to accurately get the point groups of the molecules. So this is the bonding theory you grew up with. Each bond consists of two electrons, and they're between the bonded atoms. So if I have two atoms that are bonded, there's two electrons holding them together. And it makes sense. You've got positive charges on each end. You need some electrons to attract the positive nuclei. Okay. Why is it only that two electrons can hold, say, an oxygen, which has, it has 8 protons on it, and a hydrogen? Well, sure, the hydrogen is going to be attracted. One positive hydrogen nucleus is going to be attracted to that one negative electron. But what about the oxygen? Well, the core electrons shield, most of those electrons, not completely. Okay, that's why oxygen's still electronegative, because of that lack of complete shielding of the nucleus. But yeah, we've sort of canceled out most of those 8 charges by all the core electrons. And so in the valence band, you only need roughly 2 electrons to make a bond. So that's the whole concept. And this gives us this 8 electron noble gas configuration. That's unusually stable. And we got that from the first ionization energies. We had that chart where all the noble gases were really hard to ionize, and all the alkali metals were across the bottom. It was super easy to ionize. And then stable molecules will have many atoms that have 8 electrons nearby. So again, this is that octet rule specifically for carbon, nitrogen, oxygen, and fluorine. Those really hold on to the octet rule because those are the smallest nuclei up in the nonmetals region. So they're going to be the ones that are taking on electrons. How many do they want? They want 8 around them. And then the periods greater than 2, so period 3 on down, they can have larger electron clouds. And so we can expand that octet. And that's what they used to say when I was in your shoes. They called them expanded octets, which is an absolutely stupid phrase because 10 is not 8, right? So there's no such thing as an expanded octet. You could maybe say expanded valence. And so the new term is an expanded valence. So for phosphorus, you can have phosphorus pentachloride, right? Phosphorus, if you look at the column that it's in Roman numeral 5. So it's a group 5 element. So it has 5 valence electrons, and you can put a chlorine on each one of those and make this trigonal bipyramidal structure. There's 5 vertices, and that's where the chlorides are, and the phosphorus in the middle. But you can't make the nitrogen pentachloride or pentafluoride. It's just too small. And so nitrogen really is capped out at 8. Phosphorus can go up to 10 in that case because it's sharing electrons with those chlorines. Same with arsenic and so on. So this is the local bond theory. We can practice this real quick. We'll do that in a second. So this is the procedure. You sum the valence electrons, create the single bonded network, often around a central atom, subtract 2 electrons for each single bond, and then place the non-bonded pairs on the most electronegative atoms first. The electronegativity increases as you get closer to fluorine. We ignore the noble gases. So fluorine is the most electronegative element. Subtract those non-bonded electrons, and then if there are any remaining, you stick them in the central atom. Okay, and then you form double bonds on carbon, nitrogen, oxygen, or fluorine. Not really fluorine, but carbon, oxygen, and nitrogen to get that octet rule satisfied. So it's the double bonds. It's the octet rule that's driving the double bonding in local bond theory. Okay, so let's do this for a couple of molecules. This is super easy review. Okay, so the first thing is sum up all the valence electrons. So oxygen has 6. You see it's up in the group 6, and 2 for the hydrogen. 6 plus 2 equals 8. We form the single bond network. Okay, I'm going to draw it like a freshman. Okay. So there's my single bond network minus 4 bonded electrons. So I have 4 left, and I put them on the most electronegative element. So there's my water. Okay, and then we use VESPR, the valence shell electron pair repulsion theory, and we see 4 electron domains. The tetrahedral electronic structure. And I'm going to underline electronic because this is not a tetrahedral molecule. Okay, this is around that oxygen. The 4 electron domains will be on a tetrahedral arrangement, and so that gives us a bent molecular structure. Uh-oh, can't spell. So there's a big difference between the electronic structure and the molecular structure. So this is, we would call this a bent molecule, not a tetrahedral molecule. So the only place tetrahedral comes in with relationship to water is those 4 electron domains. In VESPR theory, forms a tetrahedral arrangement. Okay, let's do CO2. First, any questions about water? Again, we've been doing this for the flow chart. We had a whole lab on it. But not to discount it. If you have a question, there are no dumb questions except the ones not asked. Okay, so we have 2 times 6 for the oxygens plus 4 for the carbon. So 2 times 6 is 12, 13, 14, 15, 16. 16 electrons. All right, so we're going to do carbon, oxygen, oxygen. So then we're going to put these extra 12 electrons on the most electronegative atoms. So that's easy. Oxygen. 1, 2, 3, 4, 5, 6. We can look up there at the periodic table and see oxygen's closer to fluorine. So that's why we're picking on the oxygens. So we put 6 on each, so that's 12. So we're done. We've got all of our electrons on the molecule, but we need an octet rule for that carbon. So we start making a double bond. It's only got 4 electrons. It needs 4 more. So we're going to put 2 in from this oxygen. We'll put 2 in from that oxygen. So it's linear electronic structure and linear molecular structure. Any controversies or questions? No? So these are 2 3-atom molecules, very simple. One comes out bent, one comes out linear, right? I mean, that's from this theory, we get a bent structure for water, we get a linear structure for CO2, but both have 3 atoms. And so this theory is making a prediction about water being asymmetric and CO2 being symmetric. Water is C2V, we went through the flow chart, and CO2 is D infinity H, a very symmetric molecule. So we can go to the infrared and we can look at the infrared spectrum of air, and we see water vibrations and we see CO2 vibrations. And we know from our row vibrational spectroscopy, these are rotational lines. And so the CO2, we see this nice, beautiful P and R branch. And here we see in the bending mode, a PQ and R branch. Okay, from a linear molecule, a symmetric top, it's a very symmetric molecule. But then But then for the water, we see asymmetric, nonlinear rotational signals. So this is clear evidence that water is not symmetric. Do you see a clean P and R branch, or PQ and R branch, or P and R branch on water? No, because there's really three overlapped. Water has three rotational constants, not just one. So a linear molecule, it's lost the rotation around the axis of the molecule. That doesn't exist because there's no mass off the axis. And so it only has a rotation this way and this way. And those are exactly the same moments of inertia. So coincidentally, they have the same numerical value for the rotational constant. So really, it has one rotational constant for both those rotations. So that's why linear molecules are so easy. And we only have a P and R branch that's spaced by 2b, because we're in the infrared. Remember Hamlet. So we have the P and R branch with that single rotational constant between the lines of the P and R branch. Water, we've got rotation of all three rotations. Remember the cartwheel, the forward roll, and the spin. And each one of those has a different B value, if you will. It's really A, B, and C. And so all of those P and R branches are overlapped with each other. And so that's how water is such a mess. And so that's what you get from asymmetric molecules. So local bond theory is supported by rotational and vibrational spectroscopic data. That's why we used it to get the point groups. We had the Millikan notation for the vibrations of the molecule. We could determine the selection rules, all of that stuff. None of that would work if local bond theory wasn't good enough. But it was good enough to get the symmetry, okay? So let's look at the structure of the electron cloud. We've talked about the molecular structure, but now let's try to figure out the structure of the electron cloud, because we're making some claims about this. Let's go back and look at CO2 and water on this page here. How many types of electrons do we have? We have the non-bonded pairs, and we have the bonded pairs. So we have two types of electrons. Would everybody agree with that? Yes. About the CO2, we got to know a little bit about the pi bonding and sigma bonding. Those are separate. We did talk a little bit about that in the intro to MO theory, that the sigma bonding was end-on and the pi bonding was side-to-side, okay? And so we will calculate these single bond and the double bond as two different types of electrons. So we've got the non-bonded pairs. So that's one type. Everybody agree? It doesn't matter which oxygen you're on, that's the same type of electron. And then we have the sigmas here and here. And we have the pi's here and here. So I see three types. Everybody agree? Three types of electrons. Okay, good. We're going to have a Kahoot on that. Okay. So there's three types of electrons on the CO2 and two types of electrons on the water. So that's our electron cloud. If we were to calculate the energies of those electrons, then if it's the same type of electron, it should have the same energy. And if I'm going to put energy in and yank the electrons out, I ought to have to pay the same energy to pull a non-bonded electron out. So if there are four different non-bonded electrons, those should all line up at the same energy as I'm pulling them out of the molecule. So that's what this experiment does here, this X-ray photoelectron or UV photoelectron spectroscopy. We send in a photon source, that's the photo part, and electrons come out, that's the photoelectron. So we hit a sample, electrons come out. If we put water there, how many peaks would we see? Well, we've got two types of electrons, and so we should see a lone pair peak and an OH bonding peak. So we should see two peaks if local bonding theory or local bond theory was correct. Does everybody follow the logic, right? You got two types of electrons, they're going to be at different energies. A lone pair should be a different energy than a bonding pair. Okay, so that's it. That's that easy. And so let's take a Kahoot. Let's look at ammonia and a bunch of other molecules. And so let's go do that. I got to just get my screen switched over. Good. I know it. Put the pot. Good. It's working. Uh-oh.
Oh, trying to.
Tell you what, I'm so sick of this Wi-Fi. See if I can get my hotspot set up real quick. Hang in there. We'll get you set up. It only happens when I need it, right? Yeah.
It's like the game converts in open game. Oh, yeah.
Okay, it's back on? Okay. Okay. We hope it stays the whole time. That's in 5, 10, 15, 25. So we should have 25. 22, 23, 4, one more. There's a pancake head. Good job, Steve.
There's one more.
Oh yeah, everybody's gonna say he likes that. I'm gonna get waiting for one more. Unless if you're not in and you don't care, just say go. Or if you're trying to get in, you bet you're still trying. Maybe I miscounted. I'm gonna go. I think you can still get in.
Yeah.
Yeah. Okay. Dun dun dun. It's like a game show. So this crazy molecule, ethylene. Increasing tone makes you nervous. That it's higher. So this is ethylene. So there's carbons in the middle here. Carbon there and a carbon there. Okay. 14.3. Okay. So let's go back and look at that. How did we get 3 out of it? There's so many bonds. Well, you've got these CH bonds. So they're all the same kind of bond. So that should be 1. Then you have the sigma bond between the carbons. That's 2. And then the pi bond is 3. So even though there's a whole bunch of bonds, there's 6 different bonds, we should see 3 peaks in the UV photoelectron spectroscopy. Okay, so good job. Let's go next. See how fast everybody was. Oh, pretty much just said what this one was. See how fast how good you were listening. Got to be careful because there's some tricks in there. Do y'all just have the colors on yours, like the little shapes, not the text? Yeah, be easier if they put the text on there too. So these others had like a sigma HH. There's no HH bonds, and here there was a pi HH. It just there's no way hydrogen bonds can pi. Yeah, they have no p orbitals. All right. A little bit of a mix up. So she's like, it's okay. All right, so let's see. How many valence band UVPS peaks would be for CO2? Fast thumbs. I only give you 10 seconds on this one. Or no, I guess I did 20. There you go. Good job. Well, about 50-50, actually. Not so good. Okay, let's look at that video. Yeah, it's a 50-50 split. Okay, so we've got The sigma bond, even though it's there's two sigma bonds, it's a carbon-oxygen sigma bond on either end, so that's one. Then there's a carbon-oxygen pi bond on either end, so that's two. And then not shown, because chemists are lazy, is all the dots, the lone pairs. So 3, 4, 5, 6, 7, 8. So there's 8 lone pairs, but they're all the same, so that would be 3. So that'd be the third one. Okay, go again. Still the fastest though. Okay, how many valence band UVP would there be in ammonia? Someone said it out loud. Can't help. We used to play charades, and this funny friend of ours, he's kind of goofy. He picked up the little thing out of the deal and he read it out loud. There was a movie called Knock Three Times. Anyway, he picked it out and he goes, Knock 3 times. Okay. Why did you do that? Oh, what? What did I do? You read it out loud, you dummy. Yeah. Okay. Last one, 5 of 5. How many valence band UVPS peaks would there be in water? And we just showed that one. Oh, so close to perfect. Yeah. Yay, Pancake Head, good job. All right. The tension. All right, Sarah pulled it off with the unicorn hat. That's nice. That's a runner up. Okay, that's great stuff. All right, I set that up just so that we would see the contrast when we get to the UV photo spectroscopy. So we're going to switch the window back to the PowerPoint slide and turn off the music. All right. So now let's look at the molecular orbital theory. Molecular orbital theory is very different. This is the MO diagram for water that you've seen many times. We showed it when we were doing the symmetry. We talked a little bit about MO diagrams for diatomics. Well, now we have a triatomic molecule, and we have two sides of the diagram still. We have the oxygen atom over here, and that's very easily understood. We have the 2s and the 2p, x, y, and z right here. So those are the atomic orbitals on oxygen. But for the hydrogens on both sides of the molecule, but we lump all the hydrogens on the left side of the diagram. And so there's two ways to combine those hydrogens. In a C2V character table, they can be together, okay? So they're expanding together and contracting together. They're not really close enough to overlap. So it's not really like a diatomic in that they would be overlapping or not overlapping, but there's still a node or not a node. So the lowest one with no nodes would be the lowest energy one, and the ones where they're out of phase would be the higher energy ones. The top one, if it's going in the molecule, you've got the C2V molecule, the y-axis is going out this way, and if the hydrogens are doing this, you see the electron densities going left and right. And so that has the same symmetry as y. That's all you have to do is find the symmetry of the electron cloud and what it's doing. It's oscillating left and right. So that's Y symmetry. So we could label that one B2. So that one's B2. This one's A1. It's symmetric with rotation, reflection, all of the things. It's top row. So top row's A1. So most of your orbitals that have no nodes are going to be top row, whatever character table you're in. So that one's top row, which is A1. That one is Y, so it's B2. And so then the A1s can mix with the A1s. So that's really nice. So we see we've got two A1s over here. We have the Z and the 2S, and we've got one A1 here. So if we come in with three A1s, we're going to have three A1s in the middle. So that's one of the important keys. Whatever you come in with, that's what you end up with. So if you come in with 5 of a certain thing, you're going to have 5 pictures, 5 ways to combine those things. And so that's they say the orbitals are conserved. If we come in with 3 orbitals mixing, we're going to have 3 mixtures of those in the middle. Because if you're drawing little pictures, how do you know if you have too many pictures or too few pictures? This is a way to know. And how do you draw the pictures? Well, you take all the A1s and combine them. So how can we do that? Well, it's very easy to combine the smallest one. So everybody, if I ask you, because of time on an exam or something, draw 3 molecular orbitals, because maybe you don't have time to draw all of them. You can always draw the cloud around the whole darn molecule. That's the lowest energy one, right? No nodes. Just go around the whole thing. That's the lowest energy MO that you can have, okay? And so that's this one, you see, and it's A1. It's the 2s in phase with the 2 hydrogens, the 1s on the hydrogens. And so they're all expanding together and all contracting together, and there's no nodes because they're never out of sync with each other. So that's this one. That's the lowest energy. What if the 2s is out of phase with the 2 hydrogens? Well, then you kind of get this one. The density is kind of on the top of the oxygen, and the hydrogens are down below. But you could also mix in a little bit of 2pz. You see the 2pz can mix in there with the 2s and the 1a's and 1sa and b, and you could get up this shape here. You see it kind of has some pz character, but the hydrogens are the same. So because the hydrogens are the same color, it's a A1. And then it's also A1 because the Z-axis in the C2V character table is A1. And so they can mix together. And then they could be out of phase, which is a bizarre picture up here. But you can see there's the color on top of the oxygen and the color on bottom of the oxygen, just like the 2pz. And the hydrogens are in phase with each other, but out of phase with the bottom color of the oxygen 2pz. Now, why is it shaped like that? It's because Gaussian has given those electrons more freedom to move around in space. And so it made that as the lowest energy combination of all of those nodes. So that's what we have. But those are the 3 A1s. Then we could mix in the Y, the 2py here, very easily with the Y combination of these two in phase. That makes sense, right? And then out of phase. Now you can't really see it very well, but inside that, this overall thing is the 2py on the oxygen, but inside are the 2 hydrogens that are out of phase with those colors. And so those are, combining in phase and out of phase gives you your 2 B2 orbitals. And then there's really like a non-bonding one here. This 2px has nothing over here to combine with. So we come in with 1 atomic orbital and we end up with 1 molecular orbital. And so I've turned the molecules sideways. The hydrogens are now coming out just so you can see the left and right nature of the 2px. So way more complicated than Lewis dot structure, Vesper shape, electron domains, tetrahedral, bent, etc. Very easily done with the local bond theory. This is not so easily done, okay? But is it correct? Let's look. So how many UV photoelectron peaks should we get out of this? We've got different orbital energies for each of those pairs of electrons. So we should see 4 peaks in the UV photoelectron spectra. So we go in, we put water in there, and we get this. We get 4 peaks out of it. And then 1 down here for the oxygen 1s. There's like 1 way down here. We see another peak, and that's the core electron. And so the spectrum matches MO theory. There's a little different order than our Gaussian, but if we go to the literature and we look this up, the photoelectron spectrum of water, this is what we get. We get this spectrum with 4 peaks instead of the 2 peaks that we predicted with local bond theory. So this is them. The middle 2 are swapped, but that's okay. It's just, this was a real cheap Gaussian calculation that I did. So if we were to get it more accurate, we probably would match experiment. Okay. And in the experimental paper, so you go, if you were to pull this paper out of the literature, you would see them label those peaks with 1B1 and 3A1 and B2 and A1. And so these are our symmetry labels. They're just lowercase, but it's A1 and then it's the B1 and the B2 and so on. So it's all of the labels that we have from our symmetry. So this is really showing that local bond theory is totally wrong. It does not accurately represent the bonding in the molecule. So a bond does not have 2 electrons between the 2 atoms. It doesn't. These are, in fact, where's the bond? Those sticks are just now just cartoons, just to kind of draw that it's associated with itself. But like, see, this thing covers all of the oxygen and the hydrogen. Is this electrons? There's 2 electrons in this cloud here, and they do not associate with any individual bond. And this one, that doesn't associate with any individual bond. And this one doesn't associate with, it's all of the whole molecule. And that's in the name. It's molecular orbital theory. Every orbital goes over the whole molecule, and there's no local bonding. There's no electrons associated with this particular bond. We'll see maybe an exception to that, maybe with a particular pi bond. Maybe there is actually like a pi bond between, say, a polyethylene molecule or something. You might be able to see, okay, there's 2 electrons associated with this carbon-carbon double bond, but it's seldom that pure. Okay, it's most of the time it's a molecular orbital because it goes over the whole molecule. So this is a problem. Hopefully you feel the cognitive dissonance. We've been using a theory this whole time that's just been disproven. Okay, and so how do we evaluate theories? Do we throw local bond theory out and just start from the beginning at freshman level and start teaching MO theory? Well, let's think about this. All theories have the following things. We have to judge them by these criteria. So they have explanatory power. And it's good to have a big explanatory power, okay? Explanatory power is sort of how well it fits the data. So you've got your scattered data, how well does it fit all of the scatter in the data? And then original and subsequent, and then there's also, this would be like the mean, squared values, the deviations from the data. You should be able to calculate the explanatory power using things like R-squared values. If you do a Beer's law plot, a calculation, you've got the scatter in the data, how well does your model fit that data? And that's your R-squared value. And then explanatory scope. This is how large and diverse the data set is. So if your theory can explain IR and UV vis, that's a bigger scope than if your model can only explain IR. Okay. And then ad hocness. We want less ad hocness. So if we have a lot of ad hoc exceptions to our theory, that's a problem. Those are alarm bells that your theory is not complete. It doesn't have a correct scope. So the exceptions or special cases would be like the octet rule and so on for local bond theory. That's an ad hoc rule. It's like, do this for all your molecules, but if it's carbon, nitrogen, and oxygen, start making double bonds because they want an octet. Those are specific cases. If you have a lot of specific cases in your model, then it's less good. So let's apply this to local bond or valence bond theory. So it does have a good explanatory power. It's big, okay? With the Vesper shapes, it accurately models molecular structures and gives us the symmetries of those, okay? The explanatory scope has a big hole in it. So local bond theory matched the rotational spectra. It gave us our rotational constants. It accurately predicts that CO2 would have 1 rotational constant and water would have 3 rotational constants. It matches the vibrational spectra with the symmetric stretches and asymmetric stretches. All of that stuff comes from local bond theory. But it does not match the electronic spectroscopy. So that's the big hole. So when we look at the electron cloud, which incidentally means the reactivity of the molecule, we should not use local bond theory explanations. So this has yet percolated its way all the way through. It's just like leaven that needs to be kneaded through the dough of chemistry. And it's not completely kneaded through the dough of organic chemistry because you still have organic chemists using local bond theory to push electrons and explain mechanisms when those hybrid orbitals don't exist. Think about that. So you're pushing electrons with hybrid orbitals and non-bonded pairs, and they don't exist. There's no non-bonded pair on a molecule. It's part of a molecular orbital. And so we're starting to see it knead through organic as we get into molecular orbital theory, and Gaussian calculations make that more possible. So you're seeing many, many more, the current generation of organic chemists start relying on Gaussian to explain what's going on in their research lab instead of just sp3 hybrids and so on. Okay. And so then ad hocness is bad. The local bond theory has this octet rule stuff. So then molecular orbital theory, it's good. It predicts molecular structures too. It matches rotational, vibrational, and electronic spectroscopy. Okay. And it doesn't, as far as I have not come across any special cases for MO theory. So there's not do MO theory this way unless you have a fluorine atom, right? Or do MO theory this way unless you have, a triple bond or something. Like there's some special rule for triple bond or something like that. There's no special rules. Now, there's some weaknesses, like we calculate bond order for diatomics, and that's really, really good. But we can't really calculate bond order for, say, water. But that's not a problem with MO theory. That's a problem with bond order, right? Trying to calculate the number of bonds a molecule has by looking at the antibonding and the bonding orbitals. And because we can't explain what an antibonding orbital is or a bonding orbital is in a complicated molecule, the theory of bond order completely fails, okay? So it's its own tiny little theory, and it doesn't do very well when you get beyond diatomics. Okay. So how do we choose between our theories, right? You don't want to be ignorant and just throw away local bond theory because it's easy. That's the big easy button, right? If you're doing vibration and rotational spectra and looking at symmetry, we can get structures. I mean, if any theory that can be as simple as adding up valence electrons and you can get the structure of DNA, that's a good theory, right? Or any other kind of complicated structure. You can build all of the structures that we deal with in chemistry using local bond theory. That's pretty good. So let's not throw it out because it's really easy. It'd be really hard to do the MO diagram for DNA. Yeah, good luck. Okay, even calculating that would be tough. Molecular orbital theory is not easy because you have to combine all the atomic orbitals, make the molecular orbitals, let the electrons have as much freedom as possible to get the accurate energy spacings and so on. And so it's not easy. But if you have to do electronic spectra, you need it. And if you're going to try to really get down to the nitty-gritty of the reactivity of the molecule, we're donating electrons to an electrophile or what have you, the organic chemistry mechanisms, you really do need to start using molecular orbital theory to explain those. So it's not easy, but then we do have Gaussian. So Gaussian can do all three, and it uses MO theory to do all three. Okay, and so that's easy. So we're back to easy. We got to load the software, which is very easy for students because we have a site license. Okay, but you get out into the world, that software is not cheap. There's some free versions and things like that, but so Gaussian is very, very useful. Any questions on this? Is this just kind of fun to kind of chew on the theories that we've been using our whole chemistry life? Yeah, fun or not fun? I see some faces that are like not so fun. Yeah. Some people say PChem's like that. You know, you study chemistry, you get to PChem, and they're like, yeah, that's wrong. Yeah, that's wrong. but it's okay. We're just digging deeper, looking under the hood, and you know. Like if you're a little bitty kid and your mom says, "Oh, there's a little squirrel under the hood running on a wheel," you know, that's your world. That's what you think is happening under the hood. And then you open the hood and you're like, "Where's the squirrel?" so we're big kid. We're opening the hood. You're like, "No squirrels." Okay. Well, that's all I've got.